Okay, so now let's look at a different piecewise function. All right, so before we were looking at a piecewise function where I had two conditions, and the conditions were that you use this function if x is less than 3, and you use this function if x is greater than 3, right? So now looking at this function, it's a little bit different here. So here I'm saying to you to use this function if x is not equal to 3. So for every other value in the real numbers except 3, I would be using this function, which is x squared minus 9 over x minus 3. And then I'm saying to you, okay, but if at the point x equals 3, I'm going to use 6. Okay, and so my point is here is that when I think about this using a number line, all right, I make my number line of x values, and so I'm saying to you the parts highlighted in green, all right, at those points, I want to be using the function x squared minus 9 over x minus 3, and except for at x equals 3, use the number 6. And so in terms of computing the limit, it's like, should we consider the left-hand limit? Should we consider the right-hand limit? You know, should we take the limit of one of these things? Like what is it exactly that we want to do? And so I want to have you recall just what does it mean? What is like a limit, right? And so I'm saying to you, as x approaches some value c, the limit tells us what output values or what function values, or in other words, what y values I'm approaching. Okay, so as x approaches 3, right, I want to find out what my f of x, what my function values are approaching. Okay, and so for all the values that are very, very close to 3 and are approaching 3, we're going to be using x squared minus 9 over x minus 3. And then to evaluate the function, to plug in 3 into the function, I want to be using 6. Okay, so the idea here is that I want to be using, to compute the limit as x approaches 3 of my function, I want to be using the x squared minus 9 over x minus 3. All right, and that's because at every point around x equals 3, I'm using this function x squared minus 9 over x minus 3. That's where I'm defined. All right, and so when you're trying to think of the limit, we want to know, again, what's going on very close and around that value that I'm approaching. All right, so that's why we're going to say, okay, well, to figure out the limit as x approaches 3 of f of x, that's just going to be equal to the limit as x approaches 3 of x squared minus 9 over x minus 3. Okay, and so now we were doing these limits before, where I want to try to plug in 3 into this limit, but notice that in the numerator I get 9 minus 9, which is 0, and then in the denominator I get 3 minus 3, which is 0. So I'm in this 0 over 0 case. All right, and so again, remember that the limit isn't equal to 0 over 0. It's just when I plugged in, I got 0 over 0. And so that's indicating to me to use one of the 3 techniques we've talked about so far, or I guess we also introduced last time the 4th technique with the trigonometric limits. Okay, so what we want to do is we want to go through that list. And so the first thing that I tell you, if you see a polynomial over a polynomial, you want to try to factor and cancel. And so in some cases you might have to expand out the terms, so you saw examples like that. But in this case, we do see a polynomial over a polynomial, so we're going to try to factor and cancel. All right, if we saw roots, we would try to multiply by the conjugate. If we saw fractions in the numerator, or fractions in the denominator, we would try to simplify those. And if we see things with trig, we think to use trig identities and important trig limits. And so when you look at this, you want to try to factor the numerator and the denominator. So here, I'm going to say, well, this is the limit as x approaches 3 of x minus 3 times x plus 3, and then this is over x minus 3. All right, and so here I see that these x minus 3's cancel, and so I get this is equal to the limit as x approaches 3 of x plus 3, which is equal to, and so now I'm going to try to plug in my 3 and I can get that this is 6. So now, once you produce cancellation, remember to plug in the value there. Plug in 3. Okay, so I figured out what that limit is. And so now I want to know, is it continuous at x equals 3? Alright, so I can't answer this yet. I only did one part of checking. Alright, I figured out that the limit does exist. Now, I need to figure out, is f defined at x equals c, and is it equal to the limit value? Alright, so let's check it. Okay, so I'm going to note to you that yes, this function is defined at x equals 3, right? Because I'm saying to you, when x equals 3, your output value is 6. So here, I'm saying to you, note, f of 3 is equal to 6. Right, so we check the first condition. My function is defined at x equals 3. All right. And so I know that the limit exists. Oops. X approaches 3 exists and is equal to 6. And so we see that the limit as x approaches 3 of f of x is equal to f of 3, which is 6. So we see that f is continuous at x equals 3. Okay, so even though it didn't look like it was gonna, be continuous, alright, because it's a piecewise function, you guys are used to when we graph piecewise functions, there's some sort of discontinuities going on there. So this is where it becomes important with the calculus, your calculus knowledge, to figure out the limit as x approaches 3, and to figure out, is my function even defined at 3? All right, and once you figure those things out, you want to check, are they equal to each other? In this case, yes, right? Because my function at 3, my output value is 6, so f of 3 is 6. So I checked the first condition. The second condition was to make sure the limit as x approaches 3 of f of x exists, and it does, it's equal to 6. And so since the limit as x approaches 3 of f of x is equal to f of 3, and so it doesn't really matter that it's 6, but I'm just saying it's equal to 6, we see that the function is in fact continuous at x equals 3.